Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO, FDM wireless communications. And in the last module what we had seen is that the bit error rate in a multiple antenna system decreases at the rate of 1 over SNR to the power of L, and we had said that this arises due to the fact that the probability of deep fade in the system with L antennas is proportional to 1 over SNR raised to the power of L. And now let us understand why this probability of deep fade is 1 over SNR to the power of L in a system with L antennas. So now if we will look at a system with a transmitter and a single transmit antenna, and let us say we have a receiver with multiple receiver. Let us start by considering a receiver with a single receive antenna, and we have a link between this transmit and we have a single link between the transmit antenna and the receive antenna. And if this link is in a deep fade, then the system is in a deep fade. That is, if the link is in a deep fade, then the corresponding wireless communication system is in a deep fade. And we said that the probability of deep fade for this single link is basically proportional to 1 over SNR, or the probability of deep fade is equal to 1 over SNR. So we have a single link. When we have a system with a single transmit antenna and a single receive antenna, we have a single link, and we said that the probability of deep fade for this single link is 1 over SNR. Now let us consider a multiple antenna system and see what happens in the multiple antenna system. In the multiple antenna system, we have a single transmit antenna However, we have multiple we have a single transmit antenna. However, we have multiple receive antennas. So there are L links in this system. There are L links in the system, and let EI denote the event that link I is in a deep fade. So we are saying there are L links I equal to 1, 2, 3 up to L, and we are denoting by EI the event that link I is in a deep fade. For instance, E0 is the event that link 0 is in a deep fade, E1 is the event that link 1 is in a deep fade, and so on. And now we know that the probability that link I is in a deep fade, that is the probability EI is equal to 1 over SNR. Therefore, we also know that the probability of EI, that is the link I is in a deep fade, is equal to 1 over SNR. And therefore, we can say that the probability of each link in deep fade E0 equals 1 over SNR, probability of E1 equals 1 over SNR, so on and so forth. Probability of EL equals 1 over SNR. Probability that link L is in a deep fade is equal to 1 over SNR. So, the probability of each event EI, where EI denotes the event that link I is in a deep fade, is 1 over SNR. Now, we know that the wireless system with L antennas is in a deep fade only when all the links are in a deep fade. So, the system with multiple antennas is in a deep fade. So, for system to be in deep fade, all links have to be in a deep fade. For instance, let us look at my system and with multiple receive antennas with various links, and for this system to be in a deep fade, what we are saying is that all the links, all the L links have to be in a deep fade, that is all L links but EI is the event that link I is in a deep fade. Therefore, what we are looking is that we are looking at the intersection of all these events E1, E2 up to EL. So, what we are looking at is we are looking at the intersection that is the intersection that is EI is the probability that link I is in a deep fade. Therefore, all the links have to be in a deep fade, which means basically we are looking at the intersection of these events E1, E2 up to EL, that is E1 intersection E2 intersection up to EL, and now the system is in a deep fade when all the links are in deep fade. Therefore, the probability that the system is in a deep fade is the probability of the intersection of all these events, and therefore, the probability of deep fade with L antennas equals the probability of the intersection of these L fading events. And now, if each of these events is independent, then the probability of the intersection is simply the product of the probabilities of these events. Therefore, the probability of the intersection is given as the product of the probabilities E1 times E2 so on up to the probability of EL. And now the probability, and this remember I have to clarify this, that this is arising since events, all the events EI are independent. What we are assuming is that we are assuming that the fading coefficients H1, H2 up to HL are independent. Therefore, they fade independently, and therefore, they also go into the deep fade independently. Hence, the probability that that is the event that each event EI, that is denotes that the link I is in a deep fade, all such events are independent. Hence, the probability of the intersection of these events is simply the product of the probabilities. And further, we know that the probability of EI, that the probability that link I is in a deep fade is equal to 1 over SNR for each I. So, probability EI equal to 1 over SNR. Therefore, the probability of E1 intersection E2 intersection EL, which is equal to the product E1 times probability of E2 probability of EL is simply equal to 1 over SNR. Each of these quantities is 1 over SNR. So, this is the product of 1 over SNR taken L times, and this is simply equal to 1 over SNR raised to the power of L. Therefore, the probability of deep fade, which is the probability of the intersection of these events E1, E2 up to EL, is simply equal to 1 over SNR raised to the power of L. And therefore, what we obtain is that the probability of deep fade, or the probability of deep fade with L antennas, this is equal to 1 over SNR raised to the power of L. And therefore, what we are seeing that the probability that of event EI, that link I is in a deep fade, is 1 over SNR. Therefore, the probability that all the links E1, E2 up to EL are in deep fade is simply the product of all these probabilities, which is 1 over SNR multiplied L times. Therefore, it is 1 over SNR raised to the power of L, and hence the probability of deep fade in this system with multiple antennas or with L antennas decreases as 1 over SNR raised to the power of L, because of the L independently fading channels between the transmitter and the receiver, and that is a very important aspect of this multiple antenna system or this receive diversity system with L antennas. Therefore, this probability of deep fade decreases as 1 over SNR raised to the power of L, and this is arising due to the multiple fading channels, and this is arising due to multiple independent, and that is the key, independent this is arising due to the multiple independent fading channels between the transmitter and receiver. And let us now look at this. This is also known as spatial diversity. This form of diversity, where you have diversity arising from multiple antennas, because we have the transmitter with a single antenna, we have the receiver with multiple antennas, and we have multiple links between the transmitter and receiver, that is, we have multiple antennas in space, distributed in space, that is the keyword space. Therefore, this is also known as spatial diversity. Therefore, we have these multiple antennas, multiple receive antennas which are distributed in space. Therefore, this concept, that is where you have diversity with multiple antennas, this is also known as spatial diversity. That is, you are exploiting the spatial dimension to incorporate diversity, and diversity thereby improves the reliability or decreases the bit error rate in this wireless communication system. So, this is also known as spatial diversity. And also we had seen that one key assumption in this system with spatial diversity is the independent nature of the different fading channels. So, what we have seen is that in order to have maximum diversity, one key assumption or one important assumption is all the links or all coefficients H1, H2, HL are independent or independently fading. And for independent fading, remember the antennas have to be spaced far apart, because if the antennas are placed close to each other, then the fading can be dependent or correlated. So, for the different channel coefficients to fade independently, the antennas have to be placed sufficiently far apart. So, for this to hold true, the various antennas have to be placed sufficiently far, they have to be placed sufficiently far apart, and therefore, the question is how far? How far is far? I mean, what is the minimum distance between these, or what is the minimum distance of separation between these antennas to exploit the spatial diversity or to achieve the maximum spatial diversity, which arises when these different coefficients or these different links are independently fading. So, what is the distance or what is the separation required between these multiple antennas at the receiver, and that is given as follows. That is, let us consider this system with multiple antennas at the so I have my receiver and I have multiple antennas at the receiver, and now let this quantity d denote the spacing, that is, let d, so d denotes the spacing between the antennas, that is, antennas are uniformly spaced with distance d. So, what we are saying is antennas uniformly spaced that is, so let us have this multiple antenna system, and these antennas are spaced at a distance of d, that is the inter antenna spacing is d, or antennas are spaced uniformly with a distance of d between the two consecutive antennas. So, antennas are spaced uniformly with a distance of d between two consecutive antennas, and the quantity d denotes the spacing between the two antennas. And now the condition for independently fading channels is given as for independent fading, the minimum distance, that is the minimum d required, is given by lambda by 2, that is the minimum distance of separation. This is the minimum separation. What is this minimum d? This is the minimum separation between antenna, minimum separation between antenna elements, where lambda, what is lambda? Lambda equals wavelength of the carrier, and remember we said our carrier frequency is fc, therefore lambda equals c by fc, where fc, this is the frequency of the carrier wave, and c equals velocity of light or electromagnetic wave. C is a constant which is equal to the velocity of light or the electromagnetic wave, and c is equal to 3 into 10 raised to the power of 8 meters per second in free space. So, what are we saying? We are basically saying that the minimum separation between these antennas, or the minimum distance between the antennas, is d equals lambda divided by 2, where lambda is the wavelength, and lambda, the wavelength, is related to the carrier frequency as lambda equals c divided by fc, where fc is the carrier frequency and c is a constant which is the velocity of light, that is 3 into 10 to the power of 8 meters per second. This is the minimum inter antenna spacing that is required for independent fading in order to exploit the maximum diversity, correct. And now let us look at what this distance look like in some simple scenarios. So, let us look at a simple example to understand this. So, let us look at a simple example to understand it. Consider a GSM system with carrier frequency fc equals 900 megahertz, which is basically equals 900 into 10 to the power of 6 hertz, or 900 into the 10 to the power of 6 cycles per second. And now we can ask this question, what is minimum distance required for and we can now ask this question, what is the minimum distance required for independent fading, that is the minimum distance d between the antennas, and we know that d is given as d equals lambda by 2, but for that first we have to calculate what is the value of lambda, and lambda is given as lambda equals c over Fc. We already seen C is 3 into 10 to the power of 8 meters per second, and Fc is 900 megahertz, that is 900 into 10 to the power of 6 cycles per second, and this therefore lambda equals C by Fc, which is 0.3333 meters, which is equal to 33.33 centimeters. So, the wavelength lambda, which is the, remember lambda which is the wavelength of this system is equal to, or this carrier wave at 900 megahertz in the GSM cellular network is 33.33 centimeters, and therefore, the distance is equal to lambda by 2, which is equal to 33.33 centimeters divided by 2, which is equal to 16.66 centimeters, and if I convert this into inches, this is equal to 6.55 inches. So, this is the approximate distance between the antennas for independent fading, that is distance for and you can see that 6.55 inches, that is if one antenna, is placed at a certain point, then the next antenna has to be placed at least 6.55 inches apart from it, away from it, for these two antennas to experience independent fading. And now you can see this is not possible in a regular phone, because the dimension of a normal phone is much smaller than 6.55 inches. Therefore, it is not possible unless the phone is extremely large. This is not possible in a regular phone, but it is possible for instance in a large device such as a router or a base station. Therefore, this is not possible in a regular phone because it is a large spacing, that is 6.55 inches. However, it is possible in a large device such as for instance a router or a base station, and there you can, depending on the size of the device, of course you can place multiple antennas, and if the spacing between these antennas is larger than 6.5 or approximately 7 inches, then basically these different antennas will experience independent fading and thereby exploit diversity and decrease the bit rate through diversity. Now, let us look at another example, another similar example. Let us calculate this distance. Consider now a 3G 4G system. A 3G or 4G system with, for instance, with carrier frequency Fc equals carrier frequency Fc equals 2.3 gigahertz. Now, corresponding to this you can see lambda equals C by Fc equals 3 into 10 to the power of 8 divided by 2.3 gigahertz, that is 2.3 into 10 to the power of 9. Units of velocity in the numerator are meters per second, denominator is hertz, which is per cycles per second, and therefore, this lambda is given as 0.1304 meter, which is equal to 13.04 centimeters. Therefore, the minimum spacing, minimum d required for independent fading, minimum d equals lambda by 2, which is equal to 13.04 divided by 2, that is equal to 6.5 centimeters, and in inches 6.5 centimeters is basically equal to 2.56 inches. So, at 2.3 gigahertz, remember this is the spacing that is required at 2.3 gigahertz. So, at 2.3 gigahertz, we are saying that the minimum spacing required between these two antenna elements is 2.56 inches, and now we can see that this 2.56 inches is well within the dimension of a regular phone, which is typical phones are between about 4 to 5 inches or 3 to 4 inches, or the spread of phones covers around 3 to 5 inches. So, in a typical smartphone, one can have multiple antennas or at least 2 antennas which are placed at 2.5 inches apart, and these different antennas then experience independent fading, and thus you exploiting the signals received from these two different antennas using maximal ratio combining, one can decrease the bit error rate and improve the reliability of wireless communication. So, at 2.3 gigahertz, that is in a 3G 4G system, so this is possible. So, this is possible on a phone, because 2.56 inches is well within the form factor of the current phone. So, and this is possible in a phone. So, basically we are saying that in a 3G/4G phone, which is at a carrier frequency of 2.3 gigahertz, one can have multiple antennas at a spacing of 2.56 inches, and this can be used to exploit diversity in this in such a phone. So, basically that gives you an idea of what is essential, what is the intuition behind diversity, and what is the minimum spacing required between these different antenna elements to exploit diversity in the system. So, we will stop this module here and continue with other aspects in subsequent modules. Thank you very much.